This is the last video in the SHA-256 GoLang implementation, and it is covering final value construction and output. So just a quick review: we did input and pre-processing in the first video of this series, then we did compression, and now we're doing final value construction and output. We're going to be back into our main file here. We're going to look at this last step. So we've passed all of our message blocks, all of our message schedules. We've compressed them all together through this for loop and through our compression function. And once we get our hash values back, we're calling this final function here, print final hash values in hex. And so that's this function right here. And what it's doing is it's taking in those final hash values and then it's concatenating them together as a single hexadecimal string. And so it's just taking all of its parts, so the 8 final hash values, and just putting them together as one single value. And then we can just take a quick look at what that output is. And so if we just run this here, we'll go run program, pass in ABC, and that is our output. And then we can just check it by doing an echo to open SSL SHA-256. We'll just pipe that in. And sure enough, those two values match. And so that more or less wraps up the implementation. But there are a couple of things that I just wanted to go over really quickly in addition to the implementation. So a couple of things that I should just point out, because in the next set of videos doing the RipeMD 160 implementation, there are a couple of differences. But one thing that is a bit different for the SHA-2 hash functions versus their predecessors of RipeMD, but also more so MD5, is MD5 uses little endian notation for some of its values, and RipeMD 160 actually carries that on because RipeMD uses those too. RipeMD is more or less based on MD4, and then RipeMD 160 and SHA-256 are more so based on MD5. And just to illustrate what I mean by endianness or endian format, little endian versus big endian, I'm just going to copy our final hash output value here for our string ABC, and I'm going to pull our hash calculator over here, and if we paste that in, we know that that's a hex input, and we're not going to hash it, we just want a hex output. But we can just say that this is in big endian for right now, and if we switch this to little endian and we click calculate hash, we'll see that this looks a little bit different. And so what's happened here is the bytes, and since this is in hex, 2 letters or 2 characters denote 1 byte because it's base 16. And so what's happening here is the bytes that were on the leftmost part here have been switched to be on the rightmost part. And so what endianness does, what it's denoting here, is which side of this array of bytes is the most significant. And so generally human beings like to read things in big endian format. That's how we, or at least in the Western world, that's how we read most of our information from left to right, and from largest significance to smallest. So like when you think of decimal numbers and you're looking at regular digits, like the number 1000 is written like that. So the thousands is on the left hand side. That's the most significant one. That's the most significant digit. And then the ones is on the right hand side. And so what little endian does, this is big endian notation, and what little endian does is it switches that around. So it would look like this. And this would be the ones. It's still the ones, and this is the tens, and this is the hundreds, and this is the thousands, but it's just arranged differently. So the reason why there's different endianness in computer systems is because when you have bytes listed in little endian, it actually makes hardware slightly easier to design because of the way processors read in memory. But at the same time, it also makes things a little bit more difficult to read. So it was agreed upon that internet and networks will always use big endian values, but you have quite a few processors and computer systems that use little endian values. And it really doesn't matter all that much what the endianness is, as long as the system that's using that endianness is consistent with it. Where you run into problems is if you're trying to communicate between two different systems that are using two different endianness systems or endianness notations, but there's different ways you can get around this, and it really just comes down to consistency. Maybe just a fun little tip at the end here too is the word endianness actually comes from the book Gulliver's Travels, where there was a big war that broke out between two factions in the book over which way a boiled egg should be eaten, either the little end up or the big end up. And so you have little endian and big endian, and that's where the name comes from. It's kind of silly, but it's also a little bit fun. And so that wraps up our implementation of SHA-256. I hope you found this useful and helpful, and hopefully it gave you a good idea of what's actually happening inside of SHA-256, inside of a hash function, and made it a little bit less mysterious and daunting. And I'll see you in the next chapter.